So the idea behind this is that some networks have this so-called community structure. They're divided up into some groups like this. There are little dense cliques in the group joined together by sparser connections. So I'm actually not going to talk very much in this talk about whether this kind of structure exists in networks. I'm going to talk mostly about methodology. If it exists, I'm going to assume that it exists and say, how would we go about finding it in a network? However, there's another talk immediately after this one by Michael Mahoney from Stanford, and I gather that he's going to talk more about the data, so if that's your thing, stick around for his talk. So why might we be interested in structure like this if it exists in networks? Well, there are a couple of different reasons. First of all, we might just be interested in these modules in the network. They could be intrinsically interesting for themselves. Like in a social network, this might be a community. It might be a group of people who all know each other and interact together. In a metabolic network, it might be some sort of functional unit of closely interacting metabolites. So we might sort of be interested functionally in these modules because they help us understand something that's going on in this network. If we measure some network, we want to understand what function implies. However, there's another reason why we're interested, which is that in many cases it turns out that the different modules in a network can have quite different structures. Here's just one simple example. This is an example of a collaboration network. So there's a social network. The nodes in this network represent scientists, and this is who's collaborated with whom. This is actually scientists at the Santa Fe Institute, where I used to work in New Mexico, and there are a number of different groups in this network, sort of subject-specific groups, basically. So take a look at, for example, this top group in the picture. It's people working on agent-based models, and it's got a certain sort of structure to it. It seems like sort of fairly free-form collaboration going on in various different groups within these red nodes. And then take a look at this mathematical ecology group here, the green one, and it's clear that it has a completely different social structure. It looks like there's sort of like one leader person and maybe a group of postdocs and students around them or something like that. So if you were to just measure, summary statistics and so forth overall for a whole network, you could miss the fact that there is this heterogeneity in the network, so you're getting different structures within the different modules. So for that reason as well, it's interesting to be able to tease these networks apart and see what the different modules look like. Well, this particular picture here is a pretty clear example. You can see, actually, just look at this network, you can pretty much see what's going on, but that's not always true. Here, for example, here's a counterexample. This network is about the same size, about 100 nodes, and I claim that it's pretty difficult to see, in this case, whether there's any modular structure going on in this network. In fact, there is. It turns out there's a very strong modular structure here, but it's a much denser network, and you can't really see what's going on just by taking a look at a picture of it. So eyeballing things on the page is not a good way of solving this problem. We need some mechanism, some statistical way of analyzing the data to tell us what the groups, if any, are in our networks. So I will just mention that this problem is somewhat related to a famous problem in computer science, the graph partitioning problem, which is a problem of divide my graph into some number of groups such that the number of edges between groups is minimized. This is a well-known and well-studied problem. There are lots of approaches to this. It is sort of superficially similar to what I'll be talking about, but in practice it's actually quite different. And in particular, this problem only really works if you specify the number and size of your groups. Right? If you allow them to be free, then it doesn't really work, because then the minimum cut is the one where you put all the vertices in one group together. We want to be able to allow the network to choose where the lines are between the communities. We don't want to have to say what size they are. And that makes this problem, this community detection problem, significantly different from this older graph partitioning problem. So here's a principled way of tackling this community detection problem, and this is not my idea. I didn't make this up. I'm just going to tell you about this idea of block models, which is one of the standard approaches to this problem. This is an approach where it's basically a model selection approach. You propose a model network that has community structure in it, and then you fit that, typically by maximum likelihood, to the observed data to find out what the community parameters are that best fit the data you saw. So you create a model where you say, I have some number of vertices in my graph, 100 or 1,000,000 or whatever it is, and I'm going to put them in some groups such that G sub I is the group to which vertex I belongs. And I'm going to define probabilities for connections within and between groups. P sub Rs is the probability that there is a connection from a vertex in group R to a vertex in group S. So in other words, these groups are homogeneous. Every vertex within a group behaves the same and has the same probability of connection to other vertices in its own group and vertices in different groups. So you have this matrix of probabilities for connections within and between groups. And that specifies a network. Now I can go ahead and generate a random network from this model. So the goal is I want to calculate the likelihood of my data within this model and then maximize it with respect to, first of all, these parameters P sub Rs, which are not the parameters I'm really interested in, but I'd better do that. And then, more importantly, with respect to the group memberships, I have to decide which vertices are going to go into which groups. So that's the basic idea. Just to show you some of the details, here's one version of that idea. I can write down a probability for recurrence of my graph. So let E sub ij be the number of edges in the graph from I to j, and typically that's going to be 0 or 1. But I'm going to allow for the possibility that it's also greater than 1. So in principle, there could be more than one edge between any two vertices if they want to be. And then the probability of generation of my graph within this model is if this omega is now the expected number of edges between two groups, then I've got a Poisson distribution here of the number of edges between every pair of vertices with mean omega, which depends on the group memberships of the two vertices and on nothing else. So in other words, once I say which group this belongs to and which group that belongs to, I've got some Poisson distributed number of edges connecting them together, and I know what that is. In the limit where this mean becomes small, the Poisson distribution and the Bernoulli distribution are the same thing. So it becomes the same thing as that probabilistic model that I described in a hand-waving way on the previous transparency. But this particular setup is nice. I can now manipulate this expression into a slightly different form here, where this m sub rs is the number of actual edges between groups R and S, and n sub r and n sub s are the number of vertices in the two groups. And now it's easy to maximize this with respect to the parameter I don't know, this omega, and it just gives omega, the expected number of edges, is equal to the observed number of edges divided by number of vertices in R, number of vertices in S. Now, number of vertices in R, if I have nr vertices here and ns vertices here, then there are nr times ns places I could put an edge between those two. So this ratio is actually just the ratio of the number of observed edges to the maximum number of possible edges I could have. So a very simple interpretation. Put that expression back into the probability to get the maximum value of the probability, and then play around with it a bit. I can get this expression down here. So now I've done the maximization with respect to the parameter. The second step I want to do is maximization with respect to which vertices are in which groups, which is the thing that I really want to know here. The only term in this expression that depends on that is this last term here. Which vertices are in which groups affects this m sub rs. It affects the number of edges between group R and group S. And it affects the size of the groups, obviously. But it doesn't affect any of this stuff over here. This m, incidentally, is the total number of edges in the network. Doesn't change. That's fixed. And this down here doesn't depend on the group memberships. So actually, it's only this factor over here that I care about. So let's call that L. This is the thing that I want to maximize. That's my unnormalized likelihood function. Or I can normalize the log likelihood. The logarithm of that. Log is a monotonic increasing function, so it has its maximum in the same place. So the bottom line is, here is an objective function that I want to maximize over all possible assignments of vertices into groups. And I want to find the assignment of vertices into groups that maximizes this function here. So I could do that a bunch of different ways. You know, the most obvious way that would immediately occur to most people would be to use Markov chain Monte Carlo. You could certainly do that. In our work, we actually used a different method. We used a very simple vertex moving heuristic algorithm, which just moves single vertices between groups in an effort to maximize this thing. But it seems to work well. So as I say, this is a fairly sort of standard approach. People have been looking at this for a long time. It's well known. It's well studied. Unfortunately, it doesn't work. Okay? So it does have some nice properties. The things a statistician would like about this are the fact that it's asymptotically consistent. If you generate a network from this model and then feed it back into this calculation, it will recover for you, on average, in the suitable limit, the data that you put in. So if you generate a network that has some number of groups and then you ask this method to find those groups, it'll find them. It'll find them right. That's fine. The reason that I say it doesn't work in practice is because real networks look very unlike the networks that are generated by this model. And hence, no network generated by this model is a good fit to most real networks that you look at, and that causes the model to get pretty confused. So to give you an example of that, here's a famous network from the social networks literature from the 1970s. This is a network that was constructed by a guy called Wayne Zachary as part of his PhD thesis in the 1970s, and it's become sort of a classic in this area. It's a network that shows the members of a student club at a US university. It's actually a karate club, if you care. So it's a place where students go and practice their karate. And this is the network of friendships between the students. So the nodes represent the students and the lines represent who's friends with whom. And the reason that this is a sort of classic example is because while he was studying this network, a dispute arose amongst the members of this club. It was actually apparently about whether to raise the fees in the club. And some of them thought they should and some of them thought they shouldn't. And as a result, the club fractured into two halves, and half of them went off and they started their own club. And the contention is that if you take this network of friendships, which was measured before the dispute happened, that you should be able to predict how the club was going to break up in the future. And of course, this is exactly the kind of goal that people doing this kind of stuff have in mind. We'd like to be able to measure a network and then predict something that's going to happen from the structure we see in that network. So let's take this network and we feed it into the mechanism that I just described for finding communities in this network. And what we would hope it would do is divide the network into basically the left half and the right half, because those are the two halves that are known to have split off. So in this picture, I put one of the known factions on the left and one of the known factions on the right. But if you actually do the calculation, what you get is this. Now, the sizes of the nodes in this picture, I've made proportional to the degrees of the vertices. Degree meaning, number of connections the vertex has. So what you can see that it's done is it's divided into two groups, one of which consists of all the high degree vertices and the other consists of all the low degree vertices. So it hasn't found the thing that we wanted it to find. Here's another example. This is a network that was put together by a colleague of mine at Michigan called Lada Adamic, and this represents she's interested in online communities. This represents a network of blogs, i.e. personal websites that people post their thoughts on. And in particular, these are political blogs dealing with US politics around the time of the 2004 US presidential election. And the connections between them are which blogs link to which other ones. So they have hyperlinks that you can click on one, you can get to another one. And the claim that Adamic and her collaborator Natalie Glantz made in this paper was that you can tell the separation between the left-wing blogs and the right-wing blogs by looking at the structure of this network, that there are two very clear communities in this network, one composed of primarily left-leaning and one composed of primarily right-leaning websites. And again, the ones that they said were right and left-leaning are on the left and right of this picture, and you should be able to pick out that structure. But if you feed it into the algorithm I just described, it does the same thing again. It's not maybe so clear because there are so many nodes in this picture, but again, it's put all the high-degree nodes in one group and all the low-degree nodes in the other group. So what's going on there is that the model, as I've described it, doesn't know that there's variation in the degrees in this network. I mean, the model is just predicting that all vertices have the same average degree. So it should be very homogeneous in terms of degree. But in actual fact, it's not. These networks have very broad variation in degree. There are some very low degree nodes and some very high degree nodes. It can be a factor of 100 or 1,000 between the lowest and highest. So there's a very broad degree distribution. And the prior probability of having a connection between two nodes, if I know nothing else about it, depends on degree. It depends actually on the product of the two degrees. If I call degree ki, then ki kj, the probability of a connection between I and j is proportional to ki kj. So if I have two nodes of degree 100, they're 10,000 times more likely a priori to be connected than two nodes of degree 1. So this makes a huge difference. And what's happened is that the model has noticed this. It's noticed that there's a group of nodes, the high degree ones, that have very high probability of connection, and a group of nodes, the low degree ones, that have very low probability of connection. It says, aha, well, I can fit this structure with these probabilities you've given me. And so that's exactly what it does. It's done the right thing in a sense. It's found the model that best fits this structure, but it hasn't got the structure we were looking at. All it's done is it's divided high and low, and that's not much use to us. So the problem here is that the model doesn't know about the degrees of the nodes in the network. So you can fix this by the following simple change. I'm going to use the same model again now, but I'm going to introduce some extra parameters, one parameter on every vertex in the network, which I'll call theta sub I on vertex I, and it goes in there. In other words, the expected number of edges between a pair of vertices is now not just the omega thing, it's multiplied by theta I, theta j. What that does for you is, if you bump up the value of one of those theta i's, it's going to bump up the probability of a connection from that node to any other node. And so it's going to bump up the degree of that node. So these theta i's are going to allow you to control the degrees, and presumably the goal is to get the degrees to be similar to the ones that you see in the actual network. So we're now also fitting the degree distribution as well as fitting the community structure, and the community structure remains in this omega thing here. So you can do the same sort of calculations as before, fiddle around with it, get it into this form here. Now we're going to do the maximization in 2 steps. First, maximize with respect to omega and these new theta parameters. That gives you these results here. The omega is actually exactly the same as before, and the theta is just proportional to the degrees ki of the vertices. That's a nice result. And then you substitute that back in here, and you get an unnormalized log likelihood, which looks like this. So this is now the objective function that you want to optimize in order to detect the community structure. And it's actually very similar to the one that I wrote before. The only thing that's changed is, instead of having nr, ns, the sizes of the groups in the denominator here, I have this kappa r, kappa s, where kappa is the sum of the degrees in the groups. So it's now just sort of the number of edges in the group rather than the number of nodes. That's the only change, in fact. But it turns out to work magic. You take this thing and you optimize it, for example, applied to that Karate Club network that I showed before, and it now nicely divides it into the community on the left and the community on the right. And in fact, these are almost exactly the known communities into which the club split in real life. There's one node in the middle there that's classified wrong, but it's right on the boundary, so maybe we can forget getting that wrong. You can do the same thing with that network of political blogs that I showed, and again, totally different result from what I got before. It's now it knows about the degrees, so it doesn't have to fit those using its probability parameters, and it can use those to fit the community structure that's there, the division between the red blogs and the blue blogs. Sorry?
The left side of the brain on the left?
Yes, I don't know. I think the Republicans are using the left side brain and the Democrats are using the right hand side of the brain. I don't know. I actually know this picture must be upside down, because really, you know, blue is left wing in America and red is right wing. It's very strange. It's different from every other country, but really, technically, this should be the other way up. The blue should be on the left and the red should be on the right. Okay, very good. So you can do that. So this kind of thing works. I will mention that there are some issues here. One is that I haven't said how I decide how many groups there are, and I don't know the answer to that question. I don't want to spend a lot of time on it. However, if that's something you're interested in, please, by all means, ask me a question about it later on. I have some thoughts about it, but I don't know the answer. So that's an interesting open question, is how you decide how many groups there are. We just assumed there were 2 in this case. But I can sort of sidestep that question by taking another approach and say, well, okay, we can do this with this model. So this is one particular kind of model, this model for community structure, but there are many other kinds of structure we might think would occur in networks. And another example where we can apply the same sort of procedure is hierarchical structure. So another thing that people have talked about in networks is a hierarchical structure where the network is broken up into groups as before, but then those groups break up into smaller groups and those into smaller groups and so forth. So you're having several levels of this kind of community structure in the network. So this could potentially shed light on these structural motifs in the network, but a whole bunch of different scales simultaneously, small scales and large scales. So how could we tackle looking for structure like this in a network? Well, hierarchical structure is typically represented by a tree, or a dendrogram, as they call it in the social networks literature. So you'd have some tree here that represents splits of the network, starting with some split at the top into 2 groups, and then each of those splits into groups and so forth, going all the way down to the bottom. And at the lowest level, you just have single nodes. So this tree represents the entire succession of splits of the things into smaller and smaller things. This is only a binary tree the way I've drawn it here, but there's no reason in principle that you couldn't apply the same ideas to other trees. But let's just take the simple example of a binary tree. So now you can make a model out of this by saying, well, let me put a probability now on each of these internal nodes in the network. And that's going to be the probability of a connection between two nodes that share this internal node as their lowest common ancestor in the tree. So if I've got a node here and a node here, I say their lowest common ancestor is here. I have some probability written on that node. I look it up, and that tells me what the probability is that there's an edge between those two. So that's a sort of direct implementation of this idea of hierarchical structure. Sort of the lower your common ancestor in the tree, the more likely you are to be connected. Actually, technically, I haven't said that the probabilities increase as you go down the tree. They needn't increase, they could decrease. So you're going to have a bunch of weird disassociative structure in your network, as well as the more common assortative ones where you're stronger connected if you're closer together. So this is quite a powerful model, in fact. It turns out to work quite nicely, and it has a nice feature, I think, that the total number of parameters here is only order n, order the number of vertices in the network. In the previous case where I was talking about community structure, if you're assuming that your communities stay about the same size as your network becomes large, then you have order n squared parameters. So it becomes a very large model. So this one actually turns out to do almost as well on many real-world networks with a smaller number of parameters asymptotically. And I think probably the reason for that is because the real-world networks that we are looking at actually do have some hierarchical structure of this kind. So it's a statement about the data more than it is about the model. So you can do a similar sort of thing to the thing I talked about before. I can define these probabilities on the nodes. So that's the probability of an edge between subtrees. And then every internal node divides the nodes below it into a left and a right subtree. And I can write down L and R number of vertices in the left and right subtree, and E the number of edges between those two subtrees observed. And I can use that to write a likelihood function. Again, I maximize that with respect to the free parameter theta here, substitute the maximum back in, and find the log likelihood at the maximum, which is given by this expression here now. And again, I want to maximize this, but now I'm going to maximize it. So the thing that I'm changing now is not which vertex belongs to which group, but I'm changing the actual structure of the tree. So now I want to maximize this over all possible ways I could hierarchically decompose this network. That's a more non-trivial thing to do, maybe a less trivial thing to do than the first calculation I described. We did it by Markov chain Monte Carlo because I don't know if we can think of a better way of doing it. That means it's kind of slow, but it does have some advantages. So there's a standard sort of Markov chain Monte Carlo that you can use for sampling from ensembles of trees. It's a well-known thing. We borrowed it from phylogenetic reconstructions. The phylogenetics people have been doing this for years. Once you do that, one of the things the Markov chain Monte Carlo allows you to do is resample from the posterior distribution. So we have some probability distribution, maximum likelihood probability distribution over the possible trees now. If we can resample from those trees to get other trees that are, to get other networks that are similar qualitatively to the one that we started off with. That allows us to do a variety of fun things with these networks. For example, we can look not only at the trees that this thing generates, but we can look at so-called consensus trees. In other words, we look at the set of trees that all have reasonably high likelihood. Not just one of them. And then we can generate a tree that shows the common features that all of those have, but things that only appear in a few of those trees get averaged out. So you end up with this consensus tree which says, here's the features of the tree that I really think are there, and it doesn't do too much overfitting. It doesn't put in a lot of features that only appear in a few trees that well fit the data. Perhaps a more useful way of visualizing that is something like this. So this is actually exactly the same data as this, just drawn out in a different way. So this particular network here is an ecological network. It's a network actually of hosts and parasites. So it's some host organisms and which parasites live on them. And feeding this into this hierarchical decomposition, this is the decomposition it comes to. So these boxes here represent how it's dividing and subdividing the network as you go down. And you notice that it does some sort of smart, sensible things. Like, for example, this host here is grouped in a box with its 5 parasites, but those 5 parasites are also put in a box together. It's worked out that they all have something in common with each other, and it's put a box around them to say, I think that this is a group, even though none of them have any edges connecting them to any of the others. Right? So this is classic hierarchical structure, but it's not something that would be detected by the sort of community structure type calculation that I talked about before. So in many ways, this is a more flexible calculation that can detect other kinds of structure that were not present in the one I talked about before. You can also use this sampling from the posterior distribution to generate a bunch of new networks that are like the one you started off with. Those can be useful for a variety of things. These 2 plots here just show that those resampled networks, it turns out, reproduce many of the features of the original network, such as the distribution of vertex degrees and the distribution of minimal distances, shortest paths through the network. These are things that were not put into the model. So in this particular case, we didn't put the distribution of vertex degrees in the model, unlike what we did with the community structure, the block model. And yet, when you resample from this hierarchically structured network, you get networks that reproduce the degree distribution quite well. So apparently you don't need to put it in. This hierarchical structure somehow captures that degree distribution all on its own. But perhaps the most fun thing we can do with this is this link prediction thing. So what we've got now is a large ensemble of networks which we claim are somehow statistically similar to the one that we started off with. And a classic question that people want to answer about network data is, this is related to what Mark Hancock was talking about this morning, is are there things missing from my data? Are there links missing? So very often your data are incomplete and some of the links are missing, and you'd like to know which ones are missing. Well, we can't predict exactly which ones are missing. There's an awful lot of them there, and all we can do is sort of something probabilistic. But what we can do is we can give you a head start. We can say, here's a selection of edges which I think might be missing from this network, and then you can go and do the experiment and actually test whether those are there. And if you're looking at something like a biochemical network, like a metabolic network or something like that, this is a huge advantage to a biologist, because it takes them a lot of work to measure even one link. So they can't just go and randomly measure stuff or just measure every link in the network. It's going to take them a week's work to measure whether this link is there. They would very much like to know that they're actually going to find something, that there's a better chance of them finding something than if they just choose something at random. So the way you can do this here is you take this large ensemble of networks and you look through it and you see that there's one edge that appears in many of these networks but didn't appear in the original network that you used to generate the ensemble in the first place. So you say, under this particular hierarchical structure that I see here, I would expect some large fraction of the time this edge to be present, but actually I didn't observe that in my data set. That makes my data set a little bit weird. Maybe that's because that edge was missing. So we do that, and we use that to predict which edges are missing. You can also incidentally use it to predict false positives. You can use it to predict edges which are there but which shouldn't be there. But this is the missing ones. So this is something that people have thought about for quite a while, how to predict missing links in networks. It's certainly something people are interested in. What this plot here does is it compares the method that we proposed based on this hierarchical structure to a bunch of the other methods that have been proposed in the past. This plot here is a plot of the area under the curve of the ROC characteristic, which is basically just a way of saying how much better am I doing than if I just guessed randomly. Right? If my algorithm was equivalent to just guessing randomly, then half of the time it would do better than guessing randomly, and half the time it would do worse than guessing randomly. Right? So that means that you would get this AUC of 0.5. So that's what you get down here on the left-hand end, and then it rises along the axis here. Why is that? Well, because what's going on along the horizontal axis here is the fraction of the edges that I give the network. So what I'm going to do, what I'm doing here is a cross-validation test, basically. I take some network that I actually believe in, I remove some fraction of the edges, I feed what's left into the algorithm, and I ask if it can predict what I took out. So this is the fraction of the edges it's giving it. Here I'm giving it nothing at all, so of course it does no better than chance, and the best it does is if you give it everything. And what you can see is in all of these cases, this is for another ecological network, in all of these cases, the hierarchical structure here does significantly better than these various other methods that people have proposed. We've also tried this on various other networks. It does well on all of them. It does better on some than others, and that basically is a question of what kind of structure is really present in the network. Obviously, this hierarchical structure model works well in cases where the thing really has hierarchical structure. So I deliberately chose an example here where it clearly outpaces everyone else. But to be fair, I should say there are some examples where some of these other ones do reasonably well as well. Okay, so I have 15 minutes left. Excellent, very good. So then I wanted to talk about one other thing that we've been working on, which is sort of taking this idea but taking it a step further now, doing something sort of even more complicated with these models. So I've talked about this idea of community structure dividing vertices into groups, that those groups were defined in a very simple way. They were defined as more connections within the group than between the groups, or they were defined in terms of this hierarchical structure. They have a common probability which is defined by this internal node. But there are much more complicated ways in which I could define structure in these networks. And one that we've looked at is dividing a network up into groups, but where each group is defined by the particular pattern of connections that it has to all other vertices. So I'm now not going to say that it's defined by the fact that it's got more connections to vertices in its own group, for example. I can say that vertices in this group are defined by the fact that they have a few connections to the vertices in their own group, and a whole lot to vertices in this group, and some to these guys down here, and just not very much down here. Or any other combination. So I can have these sort of profiles that define vertices in a group. So now it's not going to be a group in a sort of the visual graph theoretical sense of here's a clump of vertices that are all connected together. It's more a group in the sense of these vertices all have something in common. What do they have in common? They have in common the set of other vertices that they choose to connect to. So, for instance, they have in common the types of friends that they have. That'd be the kind of thing that you're thinking about here. This is kind of a nice structure because it includes things like the community structure that I talked about before. Certainly one version of this is just everybody has lots of connections in their own group and not very many connections anywhere else. But it includes many other things as well, and I'll show you right at the end some examples of quite subtle forms of structure in networks that this kind of thing can pick out. Okay, so here's another kind of structure. We can make a generative model of this. The particular model that we looked at in this case was the following. So we actually did this as an analysis of directed networks. It doesn't have to be done for directed. You can do it undirected, but the particular one we did was for directed networks. So you have this pi sub r, which is the prior probability of being a group. That just sets the sizes of the groups. The crucial parameter here is this theta r sub I, which is the probability that a node in group R links to vertex I. So for every group, you have probabilities of linking to every other vertex. So the group is defined by these n parameters here, and they satisfy some obvious normalization conditions. And then I can write down a likelihood for my network and maximize it again. This time we did something different from both of the other examples I gave. I'm not really sure why. It just turned out to work well in this particular case. So for this particular model, we did neither of the previous things. Instead, we used an expectation maximization algorithm, or EM algorithm. So the idea behind that is that I have these parameters that define my model. If you tell me what the parameters are, then I can tell you the probability Q sub IR that vertex I belongs to group R. It's fairly simple to write down. It's just the prior probability that belongs to group R multiplied by the likelihood type factor, the probability that each of the edges is where you observe it to be. This A sub ij in this formula is the adjacency matrix. It's the thing which is 1 if there's an edge there and 0 otherwise. And then just normalized by the obvious thing, normalized by the sum of that over all groups, so that this adds up to 1. So that tells me the probability that a particular vertex I is in group R under this model, but only if you give me the parameters of the model, which unfortunately we don't know. How do we get those? Well, we do that by maximum likelihood. We write down the likelihood of the graph under this model, and then we just maximize it like continuous parameters. We just do the derivative and maximize it, and you can get an expression for the parameters, the pi's and the thetas, but they're in terms of these memberships of the groups, the Q sub I r, which we also don't know. So now we have two sets of equations, so self-consistence equations. This one tells us the Q's in terms of the parameters, this one tells us the parameters in terms of the Q's. So you just guess some initial starting value for your parameters, feed them in, and then you iterate backwards and forwards between these two equations, and eventually converges to something. It'll tell you the values of these parameters, but more importantly, it'll tell you the values of these group memberships. It'll tell you the probability now that each vertex belongs to each group. So we can take this, for instance, and apply it to that same karate club network that I showed you before. And it very nicely, again, finds the community structure in that. It actually does a little bit more than the other algorithm did, because now, since it's telling us the probability that each vertex belongs to each group, we can put shades on the vertices. And instead of just having black and white, there are some vertices in here that are sort of gray. It's telling us that it's mostly in this group over here, but there's some probability that it's actually in the other group. So it can also sort of tell us when there are vertices on the boundary that sort of not quite sure about which group they belong to. So this is an example of just the classic community structure, two dense groups of vertices, and certainly this method can pick out that structure. It does it just fine. We haven't told it that we're interested in finding that one particular form of structure. We didn't say that. We just fed this thing in and said, find a good fit to this rather general model, and in this particular case, it's decided that this is the fit it should come up with. But you feed it a different kind of network, it can come up with a totally different kind of structure, whatever works for that network. So here's a counter example. This is a lexical network, so it's a network of words. They're actually English words, nouns and adjectives. They are the 100 most common nouns and adjectives from the book David Copperfield by Charles Dickens, which I chose just because it was a childhood favorite of mine. And the network is word adjacencies, when words occur in adjacent positions in a sentence in the book. So in the English language, adjectives usually occur next to nouns. You sometimes get adjectives next to other adjectives, like the big red bus or something like that. And you sometimes get nouns next to other nouns, but most often you get adjectives next to nouns. So most of the adjacencies in this network are between an adjective and a noun. What that means is this network should be, roughly speaking, bipartite. It should have two groups with most of the connections between the groups and very few of the connections within the groups. So we feed this network into this expectation maximization algorithm, and it divides the thing into basically the groups of adjectives and nouns. Again, we haven't told it what particular kind of structure we're looking for in the network. We just say, go find a good fit using this rather flexible model, and it knows that it should divide it into this roughly bipartite division, not the more sort of traditional community structure division that you saw in this network. So it's good as a sort of exploratory tool, because it's a flexible model that can it will divide networks up into, whatever groups make sense within this rather flexible model. So now let me give you one final example before I finish. This is an example where, so in principle, both of these kinds of structure could have been discovered with a conventional block model, right? Both of these fit the conventional block model picture just fine. In principle, you can get them. This one here would be fit in a block model where you had high probabilities of connection between blocks and low probability of connection within blocks. But that's fine, you could do that. This one here, this final example, I don't think could be done with a block model. So this is not a real network now. This was kind of one that was cooked up deliberately to make it hard for the algorithm to see how it would do. So it's an artificial network. And what we did in this particular case was we have 100 nodes here around the edge, and we have 8 nodes in the middle. And the catch is that almost all the edges in this network are completely random. They're just placed uniformly at random without respect for anything at all. So virtually all of the edges in this network are just distraction. They're just noise. They're just there to make it hard for the algorithm to work out what's going on. Where's the signal? The signal is in a small number of edges that go between these central 8 vertices and the vertices around them. Each vertex is assigned to a group, and its group has 2 sort of leaders, keystone vertices, or people that they look up to. So everyone within that group has a connection to the leader vertex, and then they have a whole lot of random other garbage that's just there to throw the algorithm off. So all of the signal is just in who your leaders are, and the leaders are deliberately chosen to overlap. They're not unique to the groups. They're shared amongst the groups as well. So it's the particular pattern of your leaders. It's not just the fact that you're connected to one special vertex or something like that. So you feed this into your ordinary community detection algorithm, like a block modeling algorithm, and you get rubbish. The colors here show how you want it to divide up, and it hasn't divided it up into the correct groups. On the other hand, you feed it into this EM algorithm, and it quite nicely divides it. I mean, it's got a few vertices wrong here, but it quite nicely divides it into 4 groups. It's realized that 90% of the data it's given is complete rubbish, just discounted it, and picked out the signal that's present in these few remaining edges. Very good. So I'm almost out of time. Just to summarize, I've talked basically about 3 things: these block models, these hierarchical models, and then this rather general model of vertex classification, all of which can be quite nicely fit to data using maximum likelihood methods. I used 3 different maximum likelihood methods here. I used this simple vertex moving heuristic. I used a Markov chain Monte Carlo, and I used this EM algorithm. There wasn't a particular reason for that. I mean, I think it's nice to try out different methods, but basically we just used whatever worked for each individual project. There wasn't very much rhyme or reason behind that. But in each case, they seem to allow you to pick out some useful structure from data where otherwise it would be quite complicated to see what was going on. Before I end, I just want to say thank you to my terrific collaborators: Elizabeth Light, who's now at JRF at Oxford; Chris Moore, who's a professor of computer science at UNM, that's the University of New Mexico; Erin Closet, who's computer science at UC Boulder; and Brian Carr, who's current graduate student working with me at the University of Michigan, although he's actually currently on loan to Microsoft Research. We got some money from some people, and if you're interested in this stuff, we have a bunch of papers, and you can find them all on the web there. And thank you for your attention, and I'm done.
Well, we have time for a few questions. Yes.
So, Mark, as you noted, the work on stochastic block models goes back 30 plus years. How does the stochastic block model you presented differ from that from Wang and Wong in the 1987 paper in JASA?
I don't know if I know. So tell me about it.
I think it's exactly the same.
Oh, no, I do know the one. I do know the one that you're talking about. So that one is somewhat similar. That one is used for a directed graph.
Yeah.
I think. Is that correct? I'm pretty sure. Yes, I do remember this paper because we cited it in our paper.
Yeah.
So that one is somewhat similar. It had some different applications.
But they do add the degree. They have direct models for the degrees in them. And they do maximum likelihood. And in fact, give a nice iterative scaling algorithm for computing the maximum likelihood in a relatively straightforward way, and represent the entire model's exponential family form, which adds a lot to it. And there's, as you know, since then there's been an enormous amount of work, especially on choosing the number of groups, specifying uncertainty in the last 20-something years, which actually addresses a lot of the questions that you put forward.
Yeah.
I think it's really important to look at the literature first.
So I think that I think that this question about choosing the number of groups is really an important one. And as I say, I don't really know the answer to that question, but what I will say is that I don't really believe the approaches that other people have suggested. That, I mean, there are standard approaches which are basically based on calculating marginal likelihoods. And the trouble is that the marginal likelihoods they calculate, I don't believe that they're actually generating networks that are like the ones in the real world. So typically what they tend to do is they tend to give far too much weight to dense networks. And so, so I think that this is an interesting question. I think that there are still some open issues there that have to be solved.
Okay, take another question. Is that good?
Are you sure that your goal function always concave, so they always have a unique maximum?
Which one are you talking about? I mean,
Well, the first one definitely has unique.
yeah, so the first one is very
Afterwards-
simple, you can see.
Yeah, but afterwards, say, it becomes too complicated, so.
The answer is no, and in fact, there are definitely local maxima that we sometimes find in some of these problems. So it's certainly there are examples where there isn't a unique maximum, so it's possible that the algorithm could get misled and give the wrong answer. And what I would say about that is that one of the nice things about this area is that we tend to be doing the easy problems, right? The networks we're looking at tend to have fairly clear community structure, in which case these algorithms tend to find it quite easily. So you do a few random restarts and you find it quite reliably. You could certainly come up with hard problems where the community structure is really obscure and difficult to see. But in that case, a lot of people would say, well, I'm not really sure that there's significant structure, now in a practical sense in this network. If it's one of the hard problems, then it's probably not one of the ones we're interested in. So it's kind of nice in the sense that it's mostly the easy cases that we're interested in solving, and for those it works fairly reliably.
Take one more question. Walter?
How do you deal with dynamics?
You mean dynamically changing networks? Oh, well, absolutely we don't. So that's an excellent question. Could we do calculations like this on dynamically changing networks? Of course, one could trivially do that kind of thing by just taking snapshots of a network and repeatedly doing the same calculation. But that's not a good approach. It'd be much better if you can have some approach which takes into account the fact that I know this network evolved from this previous one and takes into account the correlations between the successive time steps and uses that information to get better answers out. So I don't know of an approach that does that, but absolutely that would be an interesting question.
So nothing is out there yet?
Nothing is out there that does that?
Yeah, that's it.
Oh, well, there may well be. Yes, I know. Looks like
No, there's a paper by
Mark has something.
Haneke and Zing about 5 years ago that does. Obviously, it's a very complex problem. They have a dynamic stochastic model that does that. And just an answer to the likelihood question, when this was found out because of the multimodal of the likelihoods in about 2000, people moved much more strongly using Bayesian methods, which at least to the first order would move away from the efficiencies of maximum likelihood, the multimodality of it. Most of the work done in the area right now uses Bayesian inference precisely because of the
Okay, let's stop here and thank Mark again.